I hope you have a nice sleep and ready for the third energetic day. I have been little bit tired, but I will try to be energetic. I hope other participants, they will arrive very soon. In the last lecture, we tried to understand how we have to develop an appropriate algorithm or the control system for integrating sustainable energy technologies with the objective to make hydrogen as an energy carrier. We discussed that when I presented a case study, a brief case study of one of my project, which I did at University of Jyväskylä, Finland, around 2 decades before, in which we identified that there is some problem with reference to the energy level or reference condition. That reference condition, what we discussed, is going to be required for developing the algorithm for operating such type of system. Okay. So, I thought I will share with you more of my experience on the same topic, so that you can get more in-depth analysis also. Okay. So, with reference to that, what we were talking about hydrogen economy. We have to understand that all tools which are all engineering domain knowledge which we are studying, basically we want to integrate that for our sustainable development, and we have seen that by 2050 we want, most of the developed countries want to be carbon neutral. So, here you can see that to become the carbon neutral, to have the decarbonized hydrogen society, okay, we need to replace the hydrocarbons by using hydrogen energy. Okay. So, that is a very interesting point here. So, here you can see we want to move towards the hydrogen oriented economy, and this hydrogen comes from the renewable energy sources, and at this moment let us say we are somewhere here with fossil fuel based economy, and slowly we are moving to replace this fossil fuel based economy using clean energy technology. So, here at 2030, what recently all the countries or most of the countries, they agreed that we have to increase our renewable capacity by 3 times. So, we need to have more sustainable technologies, and how they are going to contribute? They are going to contribute for the decarbonized society, and then the hydrogen, that is what we were discussing in the last lecture. Okay. So, now here you might have got a very high level overview why we were discussing that, why it is important from the engineering perspective, right, or considering the multidiscipline perspective when we want to move towards the hydrogen oriented economy for decarbonized hydrogen society. And very shortly, what we discussed in the last class about the algorithm, I am going to present that algorithm which was in real operational. Okay. Now, this is again a very high level information here, and I want to continue our yesterday's lecture today also, so that you can have a good idea in integrating the domain knowledge. So, in yesterday's lecture, we have the focus on making hydrogen as an energy carrier, correct? So, at this moment, our hydrogen is mainly coming from this process, okay? So, it means that hydrocarbon reforming is contributing significantly for hydrogen production at this moment. Around 95% hydrogen is coming from hydrocarbon reforming. But in the previous slide, we have seen that we want to make our society decarbonized. To make the decarbonized, we have to replace the hydrocarbon, and hydrogen can be a good energy carrier. But now we are participating in a course which is focusing on sustainable technology development. Of course, we are trying to learn about machine learning implementation in that one. But first we have to see that how these technology developments are happening. So, here you say to get the hydrogen from the clean energy sources, those are the renewables, solar photovoltaic, hydropower, wind. So, those are basically going to be used by through the electrolysis process by getting the electrolytic hydrogen. So, that electrolytic hydrogen, when we are using these sources, we do not have any hydrocarbon contribution, right. So, it is going to contribute very effectively towards the zero carbon society. At the same time, in some countries, they have the nuclear electricity also, and that nuclear electricity can also be used, and of course, the heat which can be taken as a byproduct from the power plant, nuclear, can also be used for reforming of, let us say, biomass, or maybe solar thermal we can use for getting that. But overall, the objective here is that what we discussed in the last lecture, making hydrogen as an energy carrier. Now, I also told you briefly in the last class that when we have this hydrogen as an energy carrier, okay, it can be used in multiple sectors. For example, transport sector, building sector, industry sectors also. So, when we consider this hydrogen, right, that hydrogen is a very good energy carrier, can replace hydrocarbon or natural gas, right. We can use this hydrogen with some slight modification in internal combustion engine. So, now here, this is a very interesting point from the engineering domain knowledge point of view. We know that our most of the transport sector is based on internal combustion engine, in which we are using petrol, diesel, but in place, so they are contributing towards the CO2 emission, significant contribution, and we have to reduce that, and we have to use the engineering knowledge for that. So, with some modification into the internal combustion engine, we can use this hydrogen as a fuel. Last year, I had the opportunity to participate into the European Union Hydrogen Week at Brussels, Belgium, and what I observed that most of the leading automobile manufacturer of heavy duty vehicles like Scania, Volvo, and all these big trucks, they are modifying their internal combustion engine in which they can use as a hydrogen fuel. So now you see how some points what we discussed yesterday, how they are going to be implemented in cooperation with the industry. Now next point here, that I have one point I have shown here, transport sector, but another very interesting point we will focus on that one, that is the fuel cell. Many of you already aware about this electrochemical reaction, fuel cells, and these fuel cells can be used for many applications, transport, stationary application into the building, and as well as in the industry also. Okay, so now we will come very soon about on the algorithm also. So don't worry. Okay. Now what I was mentioning yesterday, hydrogen is going to be required mainly for the process industries also. Why I mentioned? Because we are going to require fertilizers, and fertilizers require ammonia, and for production of ammonia we need hydrogen. Is it okay? So it means that for our sustainability of ourselves and for our next generation, we need to have sustainable food, and to get the sustainable food we need fertilizers, and for fertilizer we need ammonia, and we can get the green hydrogen through this electrolysis process. So you see how all the things, how they are integrated with each other. So this picture, it is providing you some idea about the supply of hydrogen and the demand. So if we go previous slide, in the previous slides, this IC engine technology is well established technology. Similarly, this process industries, they are also well established technology, but the fuel cells, they are not well established technology. So how the fuel cells, they are going to contribute in different application of sustainable technology development, and then how we have to control them, or how we have to use available data for doing the autonomous operation of such system, that we are going to focus today. Okay, so let's say for your assignment or for your exercises, if I give a task to develop an algorithm for such type of systems, I believe that after this lecture you will be in a position to provide me a flow chart of the algorithm. Right? I know that we can do lot of programming, but if you can make a flow chart based on your mind on the paper, that will also be quite good and good learning also. Okay? And I'm not sure that all of you are going to appear in the examination for the credit or not. No? So, I mean, for me, yeah, I have one suggestion here. Like in all the participants, they are interested, like to participate in, let's say, some quiz or some assignment or whatever the process we will follow for the evaluation. Then all of you will get the credits. Am I right? So then why not you do that? Because it is not going to be like very hard, but it will be more like an innovative thinking maybe. If you are interested, so we can organize, and there is not those who are going to participate, everyone is going to pass. That is true. Okay, don't worry about that. Nobody is going to fail. Okay, but to participate is also very important, because it is just like pass and fail. You don't have to be. So think carefully on that one. Okay. So then of course you will get the grades also. Okay. So that's up to you. Okay. So now here we are talking about the fuel cells, and this is the new, not the new, but is an upcoming technology. And I believe that during your undergraduate courses, you might have studied how this electrochemical reaction, it works into the fuel cells. Based on that electrochemical reaction and the fuel, which we are using, there are some classification of different type of fuel cells. Okay. So for example, when we are using pure hydrogen, which is going to come through electrolytic process, in which we are going to use sustainable energy technologies, that pure hydrogen can be used here. PEM stands for proton exchange membrane fuel cell, AFC stands for alkaline fuel cell. Okay. We can use some of our engineering knowledge in making methanol, ethanol by injecting hydrogen in that one, and we can use direct methanol fuel cell. And most of us, we are using portable electronics devices. For the portable electronics devices, direct methanol fuel cell can be used for supplying the power. Okay, so that is also a good point here. Then this next section here, basically all these are hydrocarbon gases. So they are going to contribute towards the CO2 emissions. So, but we know that at this moment we may not have the infrastructure available for the pure hydrogen due to the safety issues and many other things. We can use this hydrocarbon gas with injection of hydrogen more, with injection of hydrogen more, that we call it as hydrogen. Then that hydrogen can be used in solid oxide fuel cell or molten carbonate fuel cell, and those operate at very high temperature. So you definitely you will get some information that how we have to develop the control system or algorithms for that. So this molten carbonate and solid oxide fuel cell, they operate at a very high temperature, so they can be used as combined heat and power. So if suppose we are in the cold climatic countries where heat requirement is necessary for our survival, otherwise people will going to die. So such type of fuel cells like molten carbonate fuel cell and solid oxide fuel cells, they are quite good. So now here, coming back to the fuel cell, it can be used in different application, portable, transport, stationary, and so on and so forth. And in this transport sector, you might have observed that, of course, for the road I mentioned very briefly about, but in the maritime sector also, in the aviation sector also. Okay, so there is a big potential of this. Now, I just give you the very high level overview. Now, coming back to the problems which we are going to face and how we can use our knowledge for that. So we have seen that how we are going to get hydrogen produced, how we are going to deliver the hydrogen, how we are going to store the hydrogen, which type of fuel cells are going to be there, and then when we want to integrate them, what type of control algorithms are going to be required, and for that we need to do the research and development, and then only we can do the technology validation. So now, being and researchers, you have the opportunity to utilize your domain knowledge if you want to contribute towards the hydrogen economy, maybe in any sector, let's say on hydrogen production, for example. So in hydrogen production, that is the green hydrogen means getting the energy from the renewable energy sources. So you will need the information related to the prediction techniques to get the idea how much renewable energy production, maybe from the wind turbines or the solar photovoltaic system, is going to be there, and then based on the electrochemical characteristics of electrolyzer, which we can use as a technical or physics-based modeling with this prediction modeling, and we can get the idea about the hydrogen production. Correct? And with reference to that, because I will share with you some papers about the prediction of the solar, prediction of the wind, okay. Many of my students they did, and in those papers the algorithms are there, all equations are there, you can use them. So there you can see that we got this one, and on that if we put the modeling of electrolyzer, we will get that how much hydrogen production is going to be there, right. So here you see how you are going to contribute your computer engineering knowledge for getting the understanding of hydrogen production, which is very important for doing the policy work or making the planning. So after getting the idea of the production, we have to see that at what rate it is going to be produced. Accordingly, how we are going to store it, how we are going to deliver it, and where the application is going to be there, and then doing the technology validation. So here you can see in such type of system, when we are talking about the integration, that is a system integration. So when we are talking about the system integration, so different type of electronic components or the power conditioning devices will be required. Okay, so here you can use your knowledge. Let's say some of you are from the electronics background, how we can develop the power conditioning devices for the specific applications. Okay, because for every application the device component which we need to design is going to be very, very different. I will explain that. Okay, so there you can see that your electronic engineering knowledge, how it can be useful for designing that system components when we want to do the integration. Then yesterday we discussed about the safety also, because hydrogen is highly flammable and we have to be very careful. So safety is important, and then on top of that, always we need some standards codes. Without that we cannot work, right? Always there are some standards. So the codes and standards, then only we can move towards the hydrogen economy. So now you can see that if we are planning to make our society decarbonized by 2050, and already we are now in 2025, next 25 years are remaining, there will be huge number of requirements of engineers who can contribute towards the decarbonized society. So while teaching to your students, you have to give the focus that how the big requirement of engineering professionals for next 25 years is going to be there, and in which domain. Yesterday I was reading one article which was published by International Energy Agency, and I don't remember the exact figures, but the conclusion is that the existing electrical network of we have, it is going to be extended by that times, maybe in next 10 years. Means that you see all the power lines what we have, they are going to be increased by maybe double times in one decade. Let's say my number may not be correct, but it is going to increase very fast, right? So it means that for that we will be requiring the engineering professionals. Okay, so it means that core engineering domain is going to come back again. That is true. Okay, so now you got a little bit high level overview about hydrogen economy and how we can contribute. Now I am going to give you a very specific case about algorithm and how that algorithm have been developed by me and my team 25 years ago. Okay, so this is a now very interesting and real operational work. Okay, here you can see that we are integrating renewable energy sources with what objective? With objective to store the energy in the form of electrolytic hydrogen. It means hydrogen is going to work as an energy carrier. So here I am going to share my experience of working on this project. I was the lead in this project. Two projects we developed the same. One was in Canada and one was in Finland. So in this project, the idea was that if we are going to use wind turbine and solar photovoltaic sustainable energy technologies for storing the energy from these sources in the form of electrolytic hydrogen. And we want to have such type of system, autonomous, standalone, and for that how we need to have appropriate power conditioning devices and algorithms, and of course the data which we have collected or going to collect, how that data can be used for further analysis. So I am going to present you how these renewable energy systems have been integrated with the objective of hydrogen production and storing. And then here I missed one point, that should be hydrogen utilization also. And then when we are integrating all this system, how this system is going to perform based on the control system or the algorithm which have been developed and implemented for the operation of this system, and then operation and performance analysis. And then of course I am going to provide you the conclusion. Okay. So this is a very interesting project, and I feel very happy that I did this work maybe around 25 years before, and now we have seen in this hydrogen economy slide, by 2050 our fossil fuel based economy is going to be replaced with hydrogen based economy. So it means that some of the outcomes from this project is going to be useful for that. Okay, so I feel very glad that the work which me and my team, what we did 25 years before, is going to make significant contribution now. Okay, so that is so whenever you want to do any research or any work, you have to think that how that work will be useful for next 25 years or 30 years, right? And maybe more from the practical implementation point of view. And similar approach you need to follow in your teaching also. Now, the question in your mind may come that we want to store the energy in the form of electrolytic hydrogen. We can use battery bank also. So compared to battery bank, storing the energy in the form of electrolytic hydrogen is going to be more complex than conventional battery system. That is true. Okay, that is true. So, but then what advantages which we are going to get? What advantages which we are going to get? Then we know that most of the technologies, they are available into the market. But the big challenge is that how we are going to integrate them. How we are going to integrate them, right, for such type of system. And when we want to integrate them in such type of system, then the expertise of electronic engineering, power engineering, computer engineering is required. Because we need to have intelligent power conditioning devices which can help us to overcome the intermittency or to integrate the components which have different operational characteristics. Okay, so that we are going to discuss. And then, of course, we need to have proper understanding of control strategy or algorithm which can help us to have the operation of such type of system, in which the key focus is to store the energy in the long term in the form of electrolytic hydrogen, which I am going to discuss with you, that have been developed and successfully tested. Now, the point which we missed in the last lecture about the energy reference level, that also, or reference condition something, that also we are going to discuss here, and also the algorithm. Now this is a real system. This is a real operational system. And now you have to see that how your computer engineering background and electronic engineering background, which you can utilize here. I will explain you in a step by step. Okay. Here, the reference DC bus have been taken. Means whenever we have any system, right? So because all of you are well qualified and you know that to operate any system we need to have some reference level. So in this work, this reference DC bus have been used. The reference DC bus is going to help us for defining some minimum maximum energy level value, which we discussed in the last class, for operating such type of system. Is it okay? Now, yesterday I mentioned you, here we have the wind turbine. So this is a real project, okay? So it's not like a simulation study or computer-based work. It's a real work, okay? And of course, then when we do the real work, we need to have the real power conditioning devices, real operating control system, and of course, then we are going to collect the data also. Okay? Then of course, we need to do the data analysis also, and then that data analysis, then we can fit into the machine learning. So here, this energy level at the DC bus have been taken as a reference condition, and on that, this wind turbine, which is a 3-phase permanent magnet synchronous generator, have been taken into account. Its output, what we discussed in the last class, it was variable voltage, variable frequency. So by using appropriate power conditioning devices or regulators, we converted it at an appropriate voltage and appropriate DC voltage, okay, and that we connect on the DC bus. Similarly, solar photovoltaic also, okay, different operational characteristics, different type of power conditioning devices will be required, the regulators will be required to have the appropriate voltage so that we can connect here to the DC bus. So some of you are having electronic engineering background and might be working in developing some electronic components also. So here you can see that the components which are going to be required here in this case is mainly the DC-DC converter. And the role of the DC-DC converter to operate this photovoltaic array at maximum power point. And I believe that even the computer engineering students, they might have did this course in their bachelor's about electronic components also. So you know that when we are designing the DC-DC converter, if we don't do the proper calculation in finding the sizing of the system components, for example, inductor size, capacitor size, right? If we are not selecting properly, then it can operate under the discontinuous conduction mode also. Okay? So then this system is going to fail.
Currently there are standard direct bugs available, we can directly...
Correct. So always we need to find out this will operate under the continuous conduction mode, but at the same time we have to see that those available market DC-DC converters, right, those are having appropriate capacity of the photovoltaic panel which we are connecting there, or otherwise we have to make the parallel connections of that one also. So from learning point of view here, right, they are commercially available also, but we may need to make some further changes with reference to the control system or PWM switching signals of these regulators or DC-DC converters also. Is it okay? Because I think if suppose we have the photovoltaic panel or photovoltaic array, we are connecting not on the DC bus but on the AC network, then those DC-DC converter and then DC to AC converter required now as per the regulation to provide reactive power in real time to maintain the voltage quality. So to make that reactive power available from these power conditioning devices in the real condition, then you will be required real-time operational data, and based on that real-time operational data or parameters, you will be in a position to change the switching signals of DC-DC converter and DC to AC converter for providing the active power and reactive power. Then your control algorithm and data knowledge is going to come into the picture. But in this case, we are not having the AC here, we are having the DC only. So we are only taking the active power. Okay? So, but that is a very good point here. So now, these primary renewable energy sources, their prediction output is, we can predict by using wind speed prediction and putting the modeling of the wind turbine here, taking into account the power speed characteristics, and we can predict here. Similarly, with the photovoltaic system also, taking the incident solar radiation and making its prediction and taking the operational characteristics of the photovoltaic, we can predict how the photovoltaic is going to be there. So here you can see that maybe some of the tasks you will be learning from practical sessions, that how we have to do the prediction. So you can use those prediction techniques for predicting here the wind turbine. And similarly here I mentioned you, this is going to be the standalone system. In the standalone system, of course, we are going to have some specific dynamic load. Okay, so based on the historical data of the load, we can predict that how much load is going to be there. So based on those prediction of the renewables and the load, we can predict how much excess energy is going to be there, and then slowly I will come that excess energy, by using the modeling of the system components, we can predict that how much hydrogen is going to be produced. Is it okay? So now coming back to the algorithm here, or let's say the high level, we have the energy level at the DC bus here, okay, and objective is store the energy in the form of electrolytic hydrogen, supply here, load here, and of course then we need some master controller with some algorithm here. Is it okay?
Production of hydrogen is the process variable which we need to control.
We need to maximize the hydrogen production and at the same time fulfill the load demand. Because I will explain, you will get that to that point, don't worry. So now here in this master controller, it needs all the information to be wind turbine, photovoltaic output, electrical load output, requirement, energy level at the DC. Okay. Now, when this master controller has to make the decision to start the electrolytic, it cannot have the continuous process of the electrolyzer in such type of system. So to start the electrolyzer process under this algorithm, right, when we have this input here, load out, we know that, energy level at the DC bus, we know that. So making a relative comparison, if this master controller or its algorithm decides that we have or this system has this much access, based on that it can send the information to the microcontroller, which is basically controlling the electrolyte. So the microcontroller got the information or the feedback from the master controller that during a certain time period, how much excess energy is going to be available from this primary renewable energy source with reference to the load. Based on that, this microcontroller will send the information to the microcontroller. Then this microcontroller can send the information or the signal to start the process of the electrolyzer. To start this process of the electrolyzer, we need to have appropriate power conditioning device. So this appropriate power conditioning device, in this case, this is the DC bus, this is also the DC, requires the DC voltage, but we cannot connect it directly because we need to control the power flow also to the electrolyzer based on how much excess energy is available, as well as for the isolation also, we need here DC-DC transfer. And students or the participants, I should not say the students, but the participants, because already you are of a master level maybe. So here you can see, then this microcontroller based on this one do the switching signal with, right, for transferring that excess energy in that particular time period. Okay, the time period also need to define. Now you got the idea how the, because here I am mentioning we have to define some minimum and maximum. Otherwise, if we go below the minimum level, system is not working. And our maximum level also we need to put some limit always. So you got the idea that yesterday when we were talking about the algorithm, so that how that algorithm has to be built. And it was developed by my team 25 years ago. Okay, and then we implemented that, and I will show you the real operational result. Is it okay? Now, when we are sending that excess energy, right, to this DC-DC converter, and of course, then that excess energy with reference to the load available from renewable energy sources, taking into account energy level at the DC. When that excess energy is going to the electrolyzer, so what is the role of electrolyzer? The role of electrolyzer is to produce the electrolytic hydrogen. Why? Because we are storing the energy in the form of electrolytic hydrogen, and in the first slide today we have seen that by 2050 we want to make our society decarbonized. To make our society decarbonized, we may use hydrogen as a energy, and that is the key objective of our board CAN course. If you are not able to understand, just please feel free to stop. So because this was demonstration project, whenever we want to do the research, right, always we have to see how we are going to demonstrate the technology and the work to the stakeholders also. Okay? So the stakeholders, which may be general public, policymaker, professional engineers, those who are working on energy policy also, so they can give the idea, right? They can suppose this type of pilot system it is working, right? Then how we can think from the bigger picture of the. Okay? So that was also the objective behind it, not only to do the academic research in the lab, right, but to engage the stakeholders and common public so that they can, or industries also, so that they can get the knowledge and information of such type of things. And then accordingly they can think to develop the industry's policy implementation. Now here this electrolyzer, it was alkaline electrolyzer. Okay, that is again very important point. So I'm not sure that how many of you people are aware about the different type of electrolyzer. So this is an alkaline electrolyzer, which is a very well established technology, which is widely used from country to country. So this alkaline electrolyzer always it needs constant power. Always. But now technology is changing, market dynamics are changing, new renewable intermittent technologies are coming. So then further research work and demonstration work is happening to replace this alkaline electrolyzer by using proton membrane. Some of my students, they did the work on proton membrane electrolyzer, and that fits very well with the smart grid. I will explain how it is going to fit with the smart grid, because we are trying to use this machine learning for the sustainable. So, and that work which my students they did on this equivalent electrical circuit modeling of proton membrane electrolyzer that have been highly recognized by Siemens also, and then Siemens they are using that modeling in their work also for doing further analysis of the sustainable electrical energy system in which we are going to have one load as an electrolyzer. So you can see that how the work which we should do and how it should be useful to the industry and the society. From that point of view always you have to proceed further. Of course some of the students they are having the background on or working on let's say in medical engineering, so for them it may be little different, but they have to think, let them know from high level point of view whatever the work they are doing, how it will be useful to the society. So maybe now we will take a coffee break 15 minutes and then again we will start, okay, because we need that. I have lot of material. Good. So before the break, when we talked about this alkaline electrolyzer which need to have the constant power supply, but in future due to the advancement in technology and due to the technical challenges which our network is facing due to the intermittent renewable energy sources, this system component is going to be replaced by using proton exchange membrane electrolyzer. this proton exchange membrane electrolyzer in place of alkaline will be in a position to operate under the intermittent power supply also. Now here I will put that point with reference to the smart grid. In smart grid we are trying to integrate information communication technology together and also doing the demand side management and energy efficiency. In that condition, if we are going to put in place of alkaline electrolyzer, proton exchange membrane electrolyzer, then that modeling of the proton exchange membrane electrolyzer is going to be very useful for finding out the opportunities for demand side management and conditionally transferring that intermittent renewable energy for producing the electrolytic hydrogen. Now, we know that this alkaline electrolyzer is operating at atmospheric pressure. Then when there is a buffer storage tank here, this buffer storage tank is full, then this compressor starts and compresses the hydrogen at a particular pressure and store it. Then the question will come in your mind that this compressor is going to require the energy also. That energy is again going to come from the DC bus, and therefore the energy level at the DC bus is going to be fluctuating. It means that master controller is getting the dynamic data with reference to what? With reference to changing the energy level at the DC bus, with the not only with the consumption of the energy from the to the electrolyzer, but also the consumption of energy into the compressor, and at the same time this master controller is having the real time data on wind and solar photovoltaic production also, and on the electrical load production also. Then at the same time, here you can see that then this master controller has the duty, right, to predict the wind and photovoltaic production for next couple of hours also, next couple of hours production of the requirement of the electrical load also. Based on that, then this microcontroller can do that based on the prediction values, some decisions, okay, how the energy level at the DC bus is going to change and how the hydrogen production is going to be there. Now here you can see the beauty that how we are going to integrate the prediction techniques in operation of such type of sustainable energy system, in which we want to make it completely carbon neutral from the process point of view. Okay, so it means that the input is carbon neutral. Okay, of course, for the production of those equipments there may be some carbon process also, but we are not talking about the life cycle process. We are talking only from the operation process point of view. So from the operation process point of view, taking a typical example of this one, you can see that how this machine learning based prediction techniques, which we need to implement here, right, and here also, and then getting here, and based on that, of course, the load is going to be here, hydrogen is going to be produced, and here the energy level at the DC bus is going to be changed, so that we need to predict. So based on the energy level at the DC bus, what we are predicting, right? Who is going to do that one? And then accordingly, checking the condition that how much energy is going to be provided to the DC-DC converter, to this microcontroller, but at the same time taking into account the energy consumption at the compressor, and we will get the idea at what particular pressure how much capacity of hydrogen is going to be stored for next 1 hour, 2 hour, or 1 day or 2 days. Is it okay? So that's really interesting here. Okay. Now we will come from the utilization point of view, because yesterday we discussed this one, okay? But yesterday due to the time limit and I was also tired, so we were not in a position to get the complete focus on the control algorithm. But now here, with the help of this diagram, you are in a position to get the understanding how the overall algorithm and the control system is going to be operating, and how you can use your machine learning techniques for that purpose also. And then this is a very complicated work, okay? Even it may require, if you are interested, one of you can do the PhD work on this topic also, because it is a very intensive work. Now we will come to this point. We store the energy in the form of electrolytic hydrogen. So that electrolytic hydrogen can be used for different applications also. What we have seen in, before the break, we can use in the automobile sector, process industries, fuel cell, stationary applications, and so on and so forth. So let's say when we are doing some project work and doing some demonstrations, so we have always some limitation also. So in this project, the focus was that we have this standalone system and with autonomous operation. So we will try to utilize this stored energy in the form of electrolytic hydrogen as a fuel, either into the fuel cell or into the internal combustion engine coupled with electrical generator. So let's focus first on the fuel cell. So fuel cell, again it is an electrochemical device, and in which we are going to utilize the stored hydrogen, that is the pure hydrogen, as a fuel also. So when we have to start the operation of the fuel cell, that again has to be decided by the master controller. So how this master controller is going to make the decision? So this master controller is going to make the decision based on some input conditions. So what are those input conditions? How much energy is going to be available from this primary renewable energy sources, how the demand is going to be there, and based on that we have to see that how the energy level at the DC bus is there. If suppose there is a deficit available, deficit of the energy available from the primary renewable energy sources with reference to the load, and by defining some strategies of the energy level at the DC bus, it means that we don't have the excess energy. It means we are not in a position to produce or to store it in the form of electrolytic. It means that now we have the deficit, we have to utilize the stored energy in which form? Hydrogen form, for making our system more sustainable power, to operate more sustainable manner by using this stored energy. So based on all this operation, based on this all operational parameters, then this master controller takes the decision to start the fuel cell operation and provides hydrogen as a fuel, okay, and to supply the power to the load, and when it is supplying the power to the load, because due to the deficit, energy level at the DC bus is also going to be changed. Then here you see this master controller, when it sends the information to the microcontroller, so this microcontroller specifically for this fuel cell, right, and then fuel cell, it is DC device, we cannot connect directly here, so we need DC-DC converter here also for the filter. Okay, so this boost DC-DC converter switching signal has to be controlled, as well as the supply of the fuel, that is the hydrogen, is need to be controlled for fulfilling the load under the deficit condition. Now you see, from the standalone operations point of view, how our algorithm need to be adjusted. It means at one condition excess energy, second condition excess energy available from renewable energy sources, second condition deficit of energy available from renewable energy sources with reference to the load, taking into account the energy level at the DC bus. Based on that, then algorithm has to take the decision, right, and then accordingly start the operation of the fuel cell, provide the supply to fulfill the load under the dynamic condition. So this is a very interesting and dynamic work. In such type of work, we can make the decision by taking the real-time power approach also. But here we have the focus on energy level at the DC bus. It means that it is the decisions are going to be based on the energy, not on the power. So when we are going to make the decision based on the energy level, we need to implement prediction techniques because time is there. So regarding, let's say, for half an hour or 1 hour, whatever time period we are considering, during that next 1 hour period, we should have the information for the prediction of this renewables, prediction of the load, then based on that how the energy level is going to be changed, and then accordingly this master controller has the information. So we are, let's say we are on the deficit side, that how much time this fuel cell operation is going to be there. So that controller should have the capability to have some hour ahead or 2 hour ahead, 15 minutes ahead information on the earth. Now here, to get that 15 minutes or 1 hour ahead information, we can use any technique, statistical techniques we can use for prediction. Conventionally we use that one, but now we can use any other artificial intelligence technique also. So you can see here how we are doing the marriage between machine learning techniques for this sustainable energy technology, so that their marriage remains sustainable. If there is going to be problem, then there will be diversity. So we don't want that one. We want to have the sustainability. Correct? So you have to consider those points here. So I believe that many of you may be quite good expert in machine learning techniques, prediction techniques. So you can try to implement in such type of projects also. Then another very interesting thing is that this fuel cell technology, what we are looking here, is still not very well established technology from the commercial operational point of view. Why it is not? Because this is the electrochemical device, and in that platinum is used as the catalyst, and we know that platinum is very expensive, right? Due to the cost of this is very high. One point. Second point, to operate this fuel cell, there are different operational parameters. For example, humidification level, moisture content level within the membrane, or transferring the hydrogen ion from anode to cathode, so on and so forth. So all those things we need to maintain. If we are not in a position to maintain that, our fuel cell will get damaged, and when fuel cell get damaged, in which platinum as a catalyst, it will be very expensive. So we can say that this technology is still at the learning stage, or maybe at operational stage to get it more mature. Okay? So, but in place of fuel cell, if we use internal combustion engine, in which we can use the hydrogen as a fuel and coupled with electrical generator, then also we can do that one. So that was the second option of this project. This one was the first option, and this one was the second option. But most of the focus of the work, it was on this part. Okay? So this is a very, very interesting high level flow chart, maybe I can say, of this system which was operational real time. Now here I have included a single line diagram for more clear understanding of the system. With the help of this single line diagram, you can see that this is a small system and objective was here, we have the target load of 5 kilowatt peak, and to fulfill that target load of 5 kilowatt, okay, why we selected the 5 kilowatt? Because if we consider cold climatic condition for a typical house, 5 kilowatt is the typical load. Okay, that is the reason here. Okay, and it is, we just want to test this system also. So here if you can see that maybe I think it is not coming, the full picture is not coming, we have to reduce it. But here the DC bus which is at the 48 volt, and on that we use short term energy storage here, and you can see that we have photovoltaic, wind turbine integrated through power conditioning devices on the DC bus. Then we have the master controller here. Master controller has all the information, okay, and then based on that the decision has been taken, and then information sent to the buck converter. The capacity of the buck converter, it was the 5 kilowatt, right, how much excess energy is there, and then sending that information to the electrolyzer, producing the hydrogen, okay. So then of course we need to have purification and so on, then we are storing that hydrogen, okay, and of course then this master controller, I think it has been more zoom, not coming completely into the picture. So this master controller sends the signal to the electrolyzer controller also, and then in the second phase, when we don't have the excess energy from this primary renewable energy sources, then this master controller sends the information to this fuel cell controller, and then fuel cell controller utilize the hydrogen as a fuel here, okay, and as a fuel into the fuel cell system, and then provide the power to the boost converter to the DC bus and on the to the load. So you see the diagram which we have seen in the previous slide, so in a single line how we can represent that one here. Now some of you might have got some idea in your mind. When we are talking about fuel cell as a sustainable technology source, and we are using hydrogen as a fuel here. So through your basic engineering chemistry, we know that for the operation of the fuel cell, we need oxygen. Correct? Without oxygen, the process cannot be completed. So here you can see that compressed air has been used as the oxidant in the fuel cell. But in the second condition, which may come in your mind, that when we are doing the electrolysis process, in the electrolysis process, hydrogen is also produced, oxygen is also produced, and that oxygen is of really very good quality, or the medical quality I can say. So if we capture that oxygen here and use as the oxidant into the fuel cell in place of compressed air, so naturally the performance of the fuel cell is going to improve. Very simple. In place of compressed air, if we use pure oxygen as the oxidant, performance will improve. So now here, considering your machine learning approach, we can predict from the electrolyzer, based on this electrochemical reaction, how much oxygen is going to be produced and how much quantity of oxygen is going to be required for the fuel cell operation during the deficit of energy of particular that condition. That is going to be a quite interesting to see here, right? So maybe you can give this topic to your students also, right? Suppose you want to use some prediction techniques for predicting how much oxygen is going to be produced by this alkaline electrolyzer under some circumstances. Of course, we need to define, right? And then whether that produce oxygen in addition to hydrogen, how we can use here as the oxygen into the steam. So here you say how you have to think out of the box in utilizing your learning for sustainability. Then I hope that it is clear from this picture. Now we go to the second. This is a very, very interesting diagram now. In the first phase, what I was explaining you, that oxygen which was byproduct from this electrolyzer, which went to the atmosphere, if you remember correctly, if you are observing carefully in the previous slides, we sent it to the atmosphere. But in the second stage of the project, this oxygen also purified and compressed and stored. Is it okay? And then that have been utilized as the oxygen into the fuel. And then naturally, very simple, anyone can say that performance of the fuel cell will improve because we are not using compressed air, we are using pure oxygen. So naturally the process will be much more efficient. Now, coming back to this complete picture into account here, this picture or this diagram, I will explain you from the smart grid concept point of view. Okay, and smart grid is we are integrating all information communication technologies together with the objective to integrate more and more intermittent renewable energy sources and to make our energy system more sustainable. To have this microgrid operation, some of you might have studied in your undergraduate or in your master level course. We can operate such type of system using either AC microgrid approach or DC microgrid approach. AC microgrid approach, conventionally, it is quite good, but from futuristic point of view, when we are talking about hydrogen as an energy carrier, electric vehicle charging, so decentralized DC microgrid will come into the picture. That's what I feel. So this architecture of the complete system is based on DC microgrid architecture. So DC microgrid architecture operation mainly depends on what factors? Any idea? Mainly it depends on sustainability of the voltage at the DC point. If we are not in a position to keep the sustainability of the voltage at the DC bus, the DC microgrid architecture will fail. How many of you are aware about the group functionalities? Okay, I will explain you. So group functionalities are widely used in managing the power balance between existing sustainable or existing electrical energy system for its sustainable operation. Okay, so within that we know that active power and frequency fluctuations are there. So active power prediction is going to be very important, and that active power prediction can be correlated. So for how we will do the active power prediction, conventionally we are using statistical methods for that one, but now we have the all advanced technique, let's say machine learning techniques or regression based techniques and so on and so forth. So based on that, when we get the prediction of the power, real power I am talking, we can see that how the fluctuations of the frequency is going to be there within the network. So that fluctuations of the power within the network, okay, is going to depend on intermittency of renewables, load dynamics and many other things, but we have to maintain the sustainability of the power within the network. So by using this group functionality, let's say the physics based group functionality, to implement with this prediction techniques for developing or making the prediction of the controllers of the conventional generators. And when we are doing that, it means that we know that how much input power for the conventional generators are going to be required. Is it okay? So this is a very interesting point. So that is related to the AC microgrid, but here we are talking about the DC microgrid. So I will briefly try to explain you here. So when we are talking here load dynamics, okay, this load dynamics which is going to be changing with reference to the time and which we can predict, okay, and of course in your practical classes you are doing some understanding, of the prediction technique. Similarly, you can do some prediction of renewable energy also, and how the variation is going to be there. So this variation, right, so this prediction basically you are doing through using, let's say, the machine learning techniques. Maybe I think we can resume it, resume the maybe with the help of this projector. Right? Oh no, there is not less than that. No? I was trying. I cannot change the value. वन एमपी कर दो, कम करो वीडियो कर दो। हाँ बस बजे मुझे 55 आ गया, वेरी गुड, 55 पर विजिबल है कि नहीं पीछे से? No problem, don't worry. Let's make it 100. I will make it then it will be more visible. कोई नहीं, कोई नहीं. So हाँ, वो नहीं करते थे. Good. So what I was telling you here with reference to the system which we are talking, and I was trying to explain you about AC microgrid approach, and I was trying to explain you regarding the group functionality. Okay. So this group functionality conventionally it is used for changing the input to the turbine, which is basically coupled to the generator, and when this generator is providing the power which is fluctuating with reference to system. So when this power is fluctuating in real time, so naturally the real time frequency is going to fluctuate. So here you can use your machine learning techniques or statistical techniques or prediction techniques on predicting based on the variation of the load here on renewables here, that how this change in the frequency is going to be there. And conventionally we want to make this change in the frequency to 0, right? To make this frequency back into the 0 in the fraction of seconds of time, we need to have some controller which can control the fluid flow or steam flow of this turbine here. Okay, so you can see that the conventionally, okay, we are using this group functionality. If I take the change in the frequency on this axis and power on this axis, so something like that. So group functionality will be there. So this conventionally. So conventionally, this group functionality is used into the AC microgrid. But now, if we come back, if we come back on this DC microgrid here, so that technique is not going to be used. So this technique now, this is going to be the future in my opinion. Okay, in my opinion, especially for the decentralized application like electric vehicle charging station or maybe for the hydrogen energy system also, this approach or this architecture is going to play the major role. In this architecture, here we have the DC bus, here we have the voltage sustainability. Here on the AC microgrid, we have taken the change in the frequency sustainability, okay, or change in the frequency to bring it back to the sustainable value. That's what we considered here. But here in this case, it is going to be the change in the voltage on the DC bus. So how that change in the on the DC bus voltage on this DC microgrid is going to be impacting with reference to the change in the renewables input, change in the load, okay. But in this condition, we have taken the hydrogen also, so we have to take that electrolyzer as a load also. That's why I mentioned earlier, if you remember correctly, one of my students who did the modeling on proton exchange membrane electrolyzer which can operate on the intermittent level. So that modeling is going to be required, right, for prediction of change in the voltage on the DC bus with reference to all these parameters. So now you can see that how we had to utilize the component based modeling together, right, for predicting in this case especially the voltage at the DC bus. Is it okay? So just I have given you one example, or maybe you can use this task for your research project also. Or maybe like if time permits, you can prepare maybe 1 or 2 page outline on this topic. What do you think, how we can maintain the voltage sustainability on this DC bus, and why it is required, and how it is going to vary, and how you are going to predict it. Anyway, so we will move forward, because this architecture is very close to my heart, and I can speak on that, or I can teach you on maybe hours and hours, but we have the limited time. So compared to previous slide, what we have seen here, new change, that capturing the oxygen, storing it, utilizing it in the fuel cell, and producing the required electrical energy during a particular time period till it reaches a certain amount of energy level at the DC bus, taking into account the variation or prediction of this renewable and the load also. And we have to consider like this is not a simulation work, it was a real experimental work in which the control system or algorithm what we discussed today and in the yesterday's lecture was implemented. Then next point which may come in your mind, if suppose nature is not favoring us and we want to have testing of this system as a test bench, then how we are going to do that? Because sometimes nature may not favor us, we don't have the wind, we don't have the solar photovoltaic. So to overcome that, here you can see that programmable power source have been used. So this programmable power source is very important. In this programmable power source, based on taking into account the available energy resources at a particular location, we can do the prediction that one, and based on that prediction we can do some programming here in the programmable power source, and in place of wind turbine and the photovoltaic we can operate this system by using any type of intermittent supply which let us say we have predicted for a particular location. So that we can do, and then we can test the operation of such type of system. Same time here also we can use the programmable load for testing this operation of such type of system under the different dynamic conditions also. Is it okay? So I believe that you might have got some learning, right, about the operation of integrated renewable energy system with focus on hydrogen as an energy carrier. And why we have to focus on the hydrogen as an energy carrier? We have seen that hydrogen economy document. It says that by 2050 we may replace our fossil fuel based economy or making it more decarbonized. Then we have to use the hydrogen. And now in media and everywhere you might have noticed that all these leading industrialists, they are starting the big plants for producing the hydrogen. not only in India, but all over the world. And of course, the geopolitics also plays a major role on that one. Is it okay? Now, move forward. This slide is going to provide you the specific component of the system which we discussed. Like wind turbine, it was of 10 kilowatt, 3-phase permanent magnet, synchronous generator, photovoltaic array, it was small capacity 1 watt peak, 1 kilowatt peak, electrolyzer, it was 5 kilowatt alkaline, and to connect the electrolyzer to the DC bus, buck converter having the peak capacity of the 5 kilowatt, electrolyzer alkaline operating at atmospheric pressure including compressor. Similarly, fuel cell, proton exchange membrane fuel cell, 5 kilowatt capacity manufactured by Ballard. To integrate that, boost converter, okay, PWM switching signals, capacity 5 kilowatt, fuel cell operating voltage was 24, DC bus voltage was 48. So we had to design that boost converter based on that range 5 kilowatt. So you see how your electronic engineering is also going to be used for that purpose also. And then of course we need programmable load also to test such type of system under dynamics of the load also, and of course programmable power source also, and to maintain the voltage or short-term energy storage we may need battery bank on the DC bus also, and then DC source which I already mentioned, and storing the hydrogen and oxygen also. So those were the specification of this system, and maybe you can use this specification for your further research work. Let's say if you want to develop control system in which you want to use some machine learning techniques or with the prediction that how much hydrogen is going to be produced and how the energy level at the DC bus is going to be changed, how the voltage sustainability at the DC bus is going to be changed with more specific examples. Okay. Now here you can see that what I am talking, it is like a real system, is not? So here this is a 5 kilowatt electrolyzer, 5 kilowatt fuel cell, okay. So this all it comes that under the sustainable technology here, and now here you can see that big cable here, this big cable is for the wind turbine, small cable is for the photovoltaic because its capacity was small. This is 5 kilowatt fuel cell, 5 kilowatt electrolyzer, this computer we treat it as a master controller where we implemented all the algorithm. This computer, like let's say the microcontroller in which all the algorithms what we discussed systematically has programmed here to control the operation of the electrolyzer. Similarly here for the fuel cell microcontroller, this computer it works for controlling the fuel cell operation, and here it was a compressed air in the first stage, and hydrogen it as a fuel because it should not be within the lab, it was outside of the lab, okay, because we had to take into account health and safety conditions into account. Then in this master controller there is a lot of information coming from hydrogen detector sensors also. If suppose there is any leakage and like that, so then this hydrogen detectors can stop the operation to main controller or shut down the plant basically. And then of course the electrical fixtures or electrical installations within such type of lab should be flame proof, not like having any spark or anything, otherwise there may be risk, fire risk, because we never know, and health and safety should be on top priority. And on top of that, if suppose we never know if nature if we have some fault and like that, then the complete roof of the lab is to get open. So it means the hydrogen will go immediately to the atmosphere. Okay, because if we do some combustion analysis of the hydrogen using some CFD modeling and like that, so one can see that hydrogen flame goes straight off, not like this. Okay, so that also a very good part, like because for CFD analysis also we need some good computing engineering background also. Okay, so that is also very interesting. So now here you can see that how system different components they have been integrated together with different domain knowledge. Then of course this power electronics or electronics is very important, right? So these are the DC-DC converters. These DC-DC converters are used to connect, right, between the fuel cell and the electrolyzer also, between the DC bus electrolyzer and fuel cell to DC bus. Okay, so those what I have shown you. Now we will come to the results, because you are more interested now on the results of the data, let's say. Now these are the available data from this system. And under this intermittent data set, how such type of system are going to work. Because now what I believe that your objective is like to get more understanding about machine learning, and for machine learning you need the data, and for that you need some specific cases also. So here the specific cases are sustainable technology, let's say. So now here you can see, or this is for one particular typical day operation. On this particular typical day operation, let's say it started at 9 o'clock in morning, for example, until 5 o'clock. During this whole day, you can see that how the variation of renewable sources are there. So it is quite intermittent. Now, using some prediction techniques, one can predict maybe 10 minutes ahead or 15 minutes ahead prediction of this wind and PV also. But here I am just giving you the real operational data. When we have this real operational intermittent data and or input, let's say, when that input is given to the system which I described, and in that we have so many different components which you have seen now. You can see our objective was hydrogen production. Then of course when we have the deficit, we have to do the hydrogen consumption also. So here you can see that this is giving us the hydrogen. Now based on the previous values, what we have seen on the previous slides, these are the real, but you can use this data on doing the prediction of the hydrogen which we are going to be required. And that prediction of the hydrogen production, let's say, is going to be very useful for making the planning to the main controller also, how we have to operate the electrolyzer, fuel cell, how the energy level at the DC bus is going to be changed, so on and so forth, and how, not only that, how much the energy consumption is going to be there by the electrolyzer. So here, with reference to the hydrogen production, you can see that how the electrolyzer input power is also there, and you can see that renewable power, it is combined between both wind and photovoltaic. That's how it is. Okay, so you got the idea now here how such type of systems are going to be operating under the intermittent conditions. Under these intermittent conditions, of course, load is also going to play the role. Here you can see the load fluctuations are also provided here. And one more thing which might have come in your mind, that hydrogen production should be continuous. Why there is transients or regular transients are there. Right? It might have came to in your mind why the regular transients are there. So those regular transients are due to the compression, because the hydrogen flow meter was after the compression, and the compression is again consuming the energy at a particular interval when the buffer storage tank is full. So you see like how complicated it is going to be there. So it is not that easy for human operator to operate such type of system. We need to do then to have the autonomous operation. For that, our control algorithm, what we discussed earlier, should operate properly. Otherwise, the system is going to fail, and here you see how the intermittency are there. Then moving towards the next point, hydrogen consumption. Because we have seen that at some point, whenever there is a deficit from the primary renewable energy sources, okay, and then of course the energy level at the DC bus is going to be changing, and taking into account all these factors and the load dynamics also, we need to consume the energy which we stored in the form of electrolytic hydrogen, that is hydrogen consumption, for producing the fuel cell power output at the DC bus. Is it okay? Because you see both operations are there, and then when we are having such type of system in operation, we have to be very careful that there should not be simultaneous operation of electrolyzer and the. Is it okay? So now let's say if I give you a task that if you have to develop control algorithm based on prediction of the load, based on prediction of the renewables, by maintaining the voltage sustainability at the DC bus with maximizing hydrogen production, but at the same time making the reliability of the load also, because that is also our output. How you will develop a control algorithm for that one? How your flow chart should be. Maybe that should be your task, and if you complete that task as an assignment, then we will take that assignment as your examination. Is it okay? Then maybe we can see that all of you participate in the assignment process also. Because I have given you all the feedback. All the feedback I have given you, what it is going to be required and how we have to produce, how we have to proceed further. Okay? And now here, when you will develop this algorithm, so let's say you will make the flow chart, because you cannot, it is difficult to include all the machine, all the physics basic equations in the model, but let's say you will put as a block diagram there. Okay, and of course then we can take the expertise or knowledge from the domain experts also, putting those models and like that. So here you have to see, here I have given you the results for a one-day operation, but we have to run this system continuously. Okay, so this continuous operation and making the planning, we need to have some prediction, and that prediction is going to help us to whom? To the master controller in making the decisions or making a plan. Okay, and then based on that we will get the idea that how much hydrogen has been produced and how hydrogen is going to be consumed. So I think this is a very interesting topic, and you can take your time, maybe during evening time or like that. Please try to make a good assignment on this topic. So that will be really interesting for me also to see that how the participants, they are learning and what thoughts are there in their mind also. Because I may be thinking from my perspective, but you may have the different thoughts or different approach from your mindset or maybe from your background point of view also. Yes, you are saying something. No? Okay. Is it okay? So there are a lot of things, like here you can see that how the utilization factor, energy efficiency, all these factors, then of course we need to calculate, numbers are also important for us, okay. So those numbers all we did and like that. So there are a lot of things which I can discuss on this project, and the results from this project are highly recognized. They have been published widely, not only in the IEEE transactions, but in the IEEE societies also, including International Energy Agency also. And it has the work which this one was done, highly cited. Okay? And I am quite pleased that some of the work which me and my team did, let's say 25 years before, is going to be very useful for this hydrogen economy. And now Indian government is also planning, and every state they are making their plan to have more and more green hydrogen production due to geopolitical situation, or maybe commitment to the sustainable development goals, or commitment towards the net zero, or whatever there is. Okay, so this topic is quite interesting, and I request you, if time permits, please prepare one algorithm, and maybe you can carry such type of the work in cooperation with your students or PhD scholars also, if they have the interest on this topic, and I will be very happy to provide you further feedback on this topic, in which you can intelligently integrate machine learning techniques also. Very good. So shall we stop now? Good, thank you. Now we can have good lunch. On the external impact of the factor also, meteorological parameters. Some of my students, they did the work on this one also. So I will share, because we have limited time and I also get tired, but I will share those research articles with you, and then when you have the free time, you can go through them also.